Hi everybody, this is our note today on estimating instantaneous rate of change. So first I'd like you to think about what is the difference between average rate of change, which we learned about last lesson, and instantaneous rate of change. Okay, so let's think about speed. So let's think about driving to Waterloo from Leamington, let's say. So your average rate of change would be the average rate that your distance changes with respect to time. So you could be leaving UMI, be driving 60 kilometers an hour on 77, then 80 kilometers an hour. Then you get to the 401 and you're driving 100, or 120, depending on the person. Then you get to Waterloo and you have to slow down, down to 50 in certain sections until you reach your destination. So if you take the distance that you traveled, though, you're not looking at each of those speeds individually. How you would find your average rate of change is to look at your total distance it took from Leamington to Waterloo, and then you would divide it by the total time it took you to get from Leamington to Waterloo, and that would be your average rate of change, your kilometers per hour. However, the instantaneous rate of change is whatever your speed would be at any given time on that trip. It's the rate of change of distance with respect to time at an exact moment. So as you're driving down 77, whatever your speedometer says, that's your instantaneous rate of change of distance with respect to time. Or, maybe an hour later on the 401, your speed's very different. So instantaneous rate of change, again, happens at an exact instant. So take a look at this. You might have been looking at this, what I have open here. So remember the average rate of change. So let's say I wanted to find the average rate of change of between 0.5, x is 0.5, to x here. So remember, that's the slope of the secant, because it's how much does your y change, or your dependent variable, so how much does that increase with respect to how much your independent variable increased, okay? So that is what we learned yesterday. However, the instantaneous rate of change is represented by the slope of what's called a tangent. So this red line is a tangent line because it touches the curve only at the one point, okay, at this tangent point, 0.5 and then 0.25. So the instantaneous rate of change is represented by the slope of the tangent at that point. So in physics, I know that Mr. Fittler has students draw this tangent line and then use other points to estimate, use the grid here to say estimate what's another point on that line, and then use that point with this point to estimate what that slope would be. But in math, we have more precise ways of doing this. So let's talk about what happens here. So we cannot find the slope of this tangent exactly because we only know one point on the tangent line. And you know that we need 2 points to find slope. We need to do rise over run. So what we do in mathematics is look what happens when I make this secant line come closer and closer to the tangent point. Watch what's happening to the blue line. That blue line is, as we slide this point B closer and closer to the tangent point, notice that the blue line is approaching the red line. So the closer that B gets to the tangent point, the closer that the blue line is to the red line until it's pretty much exactly right on top. So the idea is we're going to find the average rate of change between 2 points that are so close together, so close to the tangent point, that it practically is the same line as the tangent line, okay? So we're going to find the average rate of change between 0.5 in this case, and then 0.5001. Those points, those x values, are so close together that they practically are the same thing, and that means that the slope of that secant line is a very, very close estimate to the slope of the tangent line. Okay, so again, as you slide this closer and closer, oh sorry, I'm moving the tangent point. As you slide the other point, the one that we're using as the second point, closer and closer to the tangent point, it gets to be a better and better estimate of what the slope of the tangent line would be, either from that direction or coming from this direction. Okay, so that's what we're going to be doing in our note today. All right, so we're going to define instantaneous rate of change, explain in words, graphically, numerically, and algebraically. Connect average and instantaneous rate of change, which I've already done verbally with you. Recognize examples of instantaneous rates of change arising from real-world situations, so like driving in a car. And use two different methods to calculate the instantaneous rate of change of functions. So there's two specific methods we're going to learn today. You need to know how to use both of them. So the instantaneous rate of change is the exact rate of change of a function y equals f at x at a specific value of the independent variable x equals a. So when I use x equals a, this a just means a specific number. Okay, so I'm using x means a general number, so x equals a means it's a specific number a. There are various ways to estimate the instantaneous rate of change. The main idea is to zoom in to find an average rate of change over a small interval of x, in fact, a very small interval of x, very close to x equals a, where a, again, is the point of tangency, the point that we want. The slope of a tangent at x equals a is equivalent to the instantaneous rate of change at that point. So a tangent, again, is a line that touches the graph only once in a small interval, and the tangent line will go in the same direction as y at that point. So we'll show this graphically in your note. This will be basically the same thing that I was showing before in the little demonstration. So if you have a curve, it doesn't matter what it looks like. This is just y equals f at x. Okay, and say that you want to find the instantaneous rate of change at point P. So that's the point of tangency, point P, and it corresponds to an x value that we'll call a. So x equals a. So this could be 2, this could be 1, it could be 3. We're just going to call that specific number a at this point. Okay, now we can draw a tangent line. So you can use a ruler. I'm going to use this line feature to draw a line through the point, but you should use a ruler. So it should it should touch P and touch the curve there only once. Okay, so it should look something like that. So this is called, and actually you should add arrows on the end. This is called the tangent line. Or actually you can just call it the tangent. And the slope of this line is the same as the instantaneous rate of change. Okay, so notice that P is going up, and so this slope is going up, so that all matches. Now, if we were to put a second point up here, Q, okay, and if you take a ruler, please, don't be like me, take a ruler and connect P and Q. That is called a secant. Okay, so its slope is equal to the average rate of change between P and Q. Okay, so the tangent is the instantaneous rate of change, the slope represents that, and a secant, its slope represents the average rate of change. Okay, so we cannot calculate the exact slope of the tangent since we only know one point. We can estimate the slope of the tangent by calculating the slope of a series of secant lines that go through the point of tangency P and points that get closer and closer to P. So, okay, so let's redraw then our function f at x. Okay, and you can pick a point of tangency P. Okay, and again, its x value, we're going to set equal to a. Okay, so you can take a ruler and draw your tangent line. Oops. Okay, make sure you draw it nice and long, okay, so you can see it. Okay, and so now we're going to show that the closer we draw our Q, okay, okay, I'm trying to figure out exactly how to do this. Okay, there's two ways of doing it. So one way is, okay, here's Q1. So its secant would be there. And then we draw an even closer Q, Q2. And its secant would be there. Notice it's getting closer and closer to being what this tangent is. And then we draw Q3. Okay, closer and closer. So the idea is that Q gets closer to P until practically there. So you can think about it sliding close to P. Okay, so that's one way of doing it, is making intervals that are just above P, okay, and that's something called the difference quotient. Okay, that's one method we're going to learn today. Another method we're going to learn is something called centered intervals. So if Q1 is a certain amount away from P, then you can do R1, which is the same amount away from P, but in the other direction. And if you connect their secants, the idea is that this secant would be somewhat close to parallel to the tangent. And then if you pick an R2, that is again an equal distance this way as Q2 is this way, that line should be even more parallel to the tangent. And R3 and Q3, again the same distance apart on either side, that should be even more close to parallel. So this method is called centered intervals. We use the word centered because it's centered like with the point of tangency in the center. So P is always in the center. Okay, and then those slopes are somewhat parallel. So again, the blue represents something called the difference quotient, where we just find one point to the right on the right-hand side that gets closer and closer and closer to P. And the green is centered intervals, so 2 points on either side of P, equidistant from P, that get closer and closer together, and you see what it's approaching. Okay, so I hope in theory you understand what we're doing. Maybe you're confused about what this is going to look like when we actually start calculating, but now we'll get going on that. So method one is using the centered interval. So that was the green example. So a centered interval has our x equals a in the middle. Make sure you write it in the middle. And we're going to have, it's going to be less than a plus h, okay, on one side, but greater than a minus h. So a is the number that's centered, and then we're going to add the same number and subtract the same number, h, so that we have an interval where a is in the middle. But we choose h to be very small. So what this looks like, if you want to draw just a quick little diagram here just to give yourself a visual for you visual learners, is if you have a curve like this, and you have your point of tangency P, okay, then you're going to choose, this is going to be a plus h, so you go a little bit that way and then a little bit this way, this is a minus h, and you're finding the slope of the secant connecting those two, and the idea is the slope of that secant is a good estimate of the slope of the tangent here because it's parallel. okay? So if we have a function like this is an exponential function, looks like it's population at time, okay? So we have 35,000 times 1.05 to the power t. They want to find the instantaneous rate of change for t equals 15. So I can interpret this to mean that it's a population of 35,000 people that's growing by 5% per year, and they want to know what rate is it growing after 15 years. So what we have to do is choose a very small value for h and find the rate of change over that centered interval. So I'm going to start with just letting h equal 1. Okay, I chose 1. It's a small number. We're going to get smaller and smaller, but I wanted to show you this. So that means that our interval is going to be between, well, so we have our t value here. So we want to find the interval between, we're going to do 15 plus 1 on this side and 15 minus 1 on this side. So between 14 and 16, what is the average rate of change? And use that as an estimation for what it would be at 15. So then the slope is p at 16 minus p at 14 all over 16 minus 14. Okay, so when you put that into the calculator, you put that into the function, you get 76,400.611 minus 69297.606. It doesn't quite fit. Oops. Divided by 2. So you get 3551.5025. Okay, so that's our first estimate, that it would be increasing by 3,551 people per year. But now we're going to choose an even smaller value of h, and we're going to see what this is approaching. Okay, so we're looking for this because does this mean that it's getting closer and closer to 3,550, or is it getting closer and closer to 3,555? We don't really know. So we need to check a few smaller values to see what this is approaching when we get closer and closer. So now we're going to choose either even smaller value of h, like 0.1. Okay, so we're going to check the interval between 15.1 and 14.9. Okay, so we added 0.1 on this side and subtracted 0.1 on this side. So now we're going to say, what is the average rate of change for p at 15.1 minus p at 14.9 divided by 15.1 minus 14.9. So when you put this into the calculator, you get 3,550.105. Okay, so it looks like it's approaching 3,550, but what if it's actually approaching 3,549? So we need to go yet one smaller value for h, okay, to make sure we know what a proper estimate is. So the key is that you need to show that the center intervals are approaching your estimated value. It's not enough to just make one guess, okay? You have to show that as the centered intervals are getting closer, that they're approaching a certain number. So now we're going to let h be 0.01. So our interval will be between 15.01 and 14.99. Okay. So our slope is p at 15.01 minus p at 14.99 divided by 15.01 minus 14.99. Okay, and when you do this, you get 3,550.1. So after 3 estimates where our h value is getting very, very small, we can see that it is in fact approaching 3,550. So that's a safe estimate for us to make now. Okay, so now we can interpret it within the situation. So therefore, the instantaneous rate of change, and you can use this short form, that's fine, is approximately, now you always have to use the word approximately because this is still an estimate, is approximately 3,550 at t equals 15. So at 15 years, so in this context, at 15 years, the population is growing by 3,550 people per year. Okay, so graphically what this looks like, I just want to make sure that you can see this here. Graphically, you know what, this isn't really a great graphical representation, so I'm going to leave the graphical representation out. But tomorrow, actually, we can show it on GeoGebra, or actually you could just go over to GeoGebra right now, which I don't know if I have open. You could go to GeoGebra right now and play around with it if you wanted to, or I can show you tomorrow. Okay, so that is a method called centered intervals. So what you're doing again is you're picking a very small value of h, going up by that value and down by that value, and then making that value of h go closer and closer. So those lines that are parallel to the tangent are getting closer and closer to the point of tangency. Okay, so the second method is called the difference quotient. Okay, and in this case, let me get this in for you. You let the point, so P, which is A, comma F at A. Okay, so that's the point of tangency. And then the second point, Q, which its x value is A plus H. And then you have F at A plus H. Be 2 points on Y equals F at X, where H is a very small number. Okay, so instead of doing intervals on either side, you're just adding very small values of H on one side. Okay, so then the slope of that is delta Y over delta X. So it is F at A plus H minus F at A, so the difference in the Y values, divided by the difference in the X values, so A plus H minus A. So we can simplify this. The top can still say F at A plus H minus F at A. Okay, but then the bottom we can just leave as H, because we have A plus H minus A, so the A's cancel out. A minus A is 0, so you just have an H on the bottom. So now we can use very small values of H in this. That's an A. All right, and we can take a look at what this looks like. So for P, so we're going to use the same function, and I'll show you how to use it for this. So we use this, again, pick a very small value of H, and find the average rate of change between the given point and this new point. So if we start with H equals 1, then our interval is between 15 and 16. Again, so we're not going 1 on either side, we're just going 1 in one direction. So our slope then is P at 16 minus P at 15 divided by 1, because our H value is 1. Or you can think about it as just what 16 times minus 15 is. So when you put this into your function, you get 3638.125. So notice that's not even really that close to what our estimate is going to end up being, as we know from before. So with the difference quotient, it really does matter that your H's get very, very small. So now let's choose a smaller value for H. So H equals 0.1. Okay, so now we're looking between 15 and 15.1. So the slope is P at 15.1 minus P at 15 all over 0.1. Okay, So if you put this into your function, you find p at 15.1. I'll show you what it is. You get 73118.363. And then p at 15 is 72762.486. And you divide it by 0.1. Here you get 3558.77. Okay? So let's get even smaller, because we don't really know what's being approached yet. So I'm going to talk about this if necessary in a second. So now we do an even smaller value of h, 0.01. So we're looking between 15 and 15.01. So our slope is p at 15.01 minus p at 15 divided by 0.01. And you put this in the function, and you get 3551. Okay, so based on this, let's take a look at what we found. Our first answer was up there, was 3638, okay? So clearly, if we had just used our first answer, that wouldn't be right at all, because we know that the better estimate is about 3550 or 3551. So that's like still quite a bit of ways away. So as we get closer, we get to 3558. So because this distance is so, or this average rate of change, or instantaneous rate of change, is so different from this one, we know that we need to make an even smaller value of h to find out what a better estimate is, because between here and here is such a big gap, so we don't really know what number is being approached. So we need to go even further. Now, really, you could go even further, because I would argue that between 3558 and 3551, sorry about that, that's still a pretty big gap. So to me, you can't really, in good confidence, give a good estimate at 3551 because there's still so much distance. So in this case, I would actually say that you need still yet a smaller value for h to show that it is actually approaching 3551. So I would still do h equals 0.01. So I would ask you guys to try that and see what you get. Okay? In either way, you should get the same as the first method, your estimate here. Okay, and the reason why it's different is because of this slightly different method, okay? So now you're going to say to me, well, Mrs. Wiens, the centered interval method is clearly much more accurate. Like, if we went back to that method, oh, the writing's gone. But if you go back to that method, you'll see that your estimates are so close to each other, really, you almost didn't even really need to do that last h value estimate. The first two were close enough that they gave you a solid estimate because you could see what was being approached. But the reason why the difference quotient is so important is because that is the beginning of calculus, and when we learn what a derivative is, you have to understand the difference quotient. So I will be asking you to use both methods, the centered intervals and the difference quotient, in this course. But the general rule is to get the best estimate, you want to make the interval as small as possible. So I started here with h equals 1 just to show you how different it could be. Really, you should never start with h equals 1. That's not a small enough estimate. Start with h equals 0.1, or even start with h equals 0.01, and then go to one smaller. 0.01 or h equals 0.001. The smaller you start, the only issue with that is that sometimes there's problems when you enter it in your calculator. People forget to put the extra decimals. That's why I often suggest this one, because it's usually accurate enough. But if you want to go nuts and you're confident with your calculator skills, you can start with an even smaller value of h. Okay? You always need to show at least 2 calculations. It's never enough in advanced functions in this course to show just one calculation with a small h. You have to show one where h gets yet smaller to show that your estimate is accurate. Okay, so now I have some practice questions here for you to try. So actually, it's just one practice question, and I want you to use the centered interval method and then the difference quotient method. So just so we're all consistent, I'm going to have you use h equals 0.1 and then h equals 0.01. Okay, your answer should be minus 9.8 for both of them in the centered interval, and that should be interpreted as meters per second. So I'd like you to try that, please. I'll be checking for it tomorrow. And then in the difference quotient, please use h equals 0.1, where your answer should be minus 10.29. H equals 0.01, where your answer should be minus 9.849. And then a third one, you should realize at this point that a third point is necessary. And you should get minus 9.8049. So because these two are getting so close together, you should be able to show here that and understand that this is approaching minus 9.8. Okay, I'd like you to think about visually why the centered interval is giving you the exact right answer both times, whereas the difference quotient isn't. And I'll give you a hint. It has to do with the fact that this is a quadratic function. Okay, so think about that and remind me to talk about it tomorrow, and I can show you on GeoGebra why that makes sense. Okay, so now take a look at the success criteria. Make sure that you are able to do those things, or maybe check off the ones you feel good about and star the ones you don't, so we can talk about it tomorrow. And hopefully through doing the homework, you can feel more confident about these success criteria. Thanks for watching. Hope you learned lots.